All right, well, welcome. Thanks for coming to this talk here. We're going to talk about system device trees, which is a way to configure hardware in embedded space, and about Lopper, which is the tool that can manipulate the device trees here. And first, I'm going to do a little bit of a short intro here in case you haven't heard about system device trees, but then we get to the meat of it very quickly. So the problem statement here is that it is really hard to configure embedded systems. There are a lot of information that a lot of different software entities, software clients need to have about the hardware. Things like the addresses of device registers, bus topologies, power topologies, and so on. So it's firmware, it's operating systems, and hypervisors, and so on. And it's been fairly ad hoc how we do that. Linux, for example, has the device trees, but other people have been doing it in different ways, include files and so on. And so we really need an industry standard and a common way so you can have one true source that describes all of this stuff. And then an easy way to be able to allocate these kind of resources as you go forward, right? And verification is also really important. It's really easy to have one part of the system that believes that, no, I own this device, and another one believes that, no, I own the device, and they both start writing at the same time. So you need to be able to verify who understands what from the system. Then go to the next slide here.
Sorry.
Yeah, there you go.
Yeah.
So what we've done here is that instead of coming up with yet another thing out there, we base this on device trees. So device trees, of course, have been around for a long time, but it really only been focused on describing the worldview from one address space point of view, one CPU, like Linux, for example. Right? So we needed to add a bunch of things so that we can describe the whole system. And so it's really two fairly separate things. We're trying to keep them separate that we are adding. One is a description of the hardware. And in that part, we're adding things like multiple CPU clusters and other masters, and that can see the address space in a little bit of a different way. And then the secondary thing is, how do you allocate, how do you configure that hardware so that, for example, Linux needs to have 1 GB memory, and then we have an RTOS that needs something else, where a device belongs. Do you want to share something, and so on. And in particular, that's really important when you have things like OpenAMP, which we talked about earlier here, where you need to have some shared pages, some shared interrupts or other mailboxes to be able to communicate. That has been really error prone if you have to put in something in a device tree in one place, and then in another place you have to put in some pound defines and stuff like that, right? What we're also trying to do is to really make sure that we are aligning this with hypervisors. A hypervisor is really just more of a virtual AMP system in the embedded space. It's very often used to divide things up between each other. So next slide.
Sorry, I'm mixing up the command, clearly.
No problem. And then we also talk about this open source tool, Lopper. Right? And the idea here is that you have this system device tree, and then you have a tool so that you can manipulate that and create traditional device tree, because we don't want to change Linux just because we're describing the whole system. Linux still needs its view of its slice of the address space, if you will, and other clients will need that as well. So this is an open source tool that's built on top of the other open source tools and libraries that are out there for device trees. And we're working on this, as I've been mentioning in another talk here, with devicetree.org. And we're working with the Linaro project, Device Tree Revolution. And then we have a special working group under OpenAMP that's driving all these things. So there are a bunch of different companies involved with this. All right, go to the next. And so the idea is that you have this system device tree that describes everything. You run Lopper, and then you get the different slices out there. And Lopper is very flexible, so you can have multiple backends. Maybe you do need to create some pound defines for an RTOS. Well, then you add your own backend that describes it exactly that way that you want to describe it. All right, next one. And this slide, very busy here, again, not going to go into all the different details, but the idea is that on the left side, you have hardware personas that defining how the hardware actually looks like. And then you have a system architect that adds information about how do I split this up? And that needs to be separated because it's different personas, different life cycles of that information. The first one is a little bit more read-only, the more you get to the right. And then you have these different, what we call execution domains. It could be one for Linux, it could be one for some firmware, could be one for an RTOS and hypervisor and so on. And they then use Lopper to create their slice of the system here. All right, so that's the introduction here. Let's go into the meat of the discussion here, Stefano.
Okay, I'm gonna talk about the latest update on the specification. So first, but let me talk about what we have been having for a while, and it's compared to the rest, is pretty stable by now. And one is a way to describe multiple cluster on a system. So that means, for instance, a Cortex-A cluster and an independent Cortex-R cluster, or a Cortex-M processor, or a microBlaze processor. And for that, we use CPU's cluster-compatible node. There is a simple example, a snippet on the right side, just to give you an idea of how it looks like. Now, these different clusters can have different address maps. So, for instance, a given hardware resource can show up at different addresses in one cluster or the other cluster. Or it might not be available at all. To be able to represent this, different mapping of resources, we have address map and indirect paths. And especially address map is useful to represent these differences in mapping. And you can see that an example again on the right. Another thing that we have been having for a while is the concept of execution domain to express what is expected to run, the set of software that's expected to run on a given cluster, plus all the hardware resources that it's expected to consume, to use. So on the right side, again, you see a little example of a domain with the CPU cluster is running on, and the execution levels, a CPU mask, things like memory ranges, and interestingly, the access list. So the access list is the list of resources that the domain is expected to access directly and uniquely, such as in this example, the CAN bus. And then Bruce will talk more in details later. There is Lopper went upstream in devicetree.org a month or two ago, and he's going to give you an update on that. So what I'm about to tell you instead is new, and we still have had feedback to address from Rob and others in the community. So this is not quite stable, but I wanted to give you an idea of where we're going and what is one of the main things that is under discussion right now in the system device tree community. And it's about bus firewalls. So what is a bus firewall? A bus firewall is something that can block DMA transactions on the SoC. So we just talked about the access list here, right? The access list here. And the CAN bus being sort of expected to be used by this reference domain. If we want to protect that access, we need a hardware capability that is provided to us by the bus firewall. And the bus firewall comes with a controller, and that is what we try to configure to be able to protect these accesses. And obviously an initial configuration. And these are the things that we're trying to all together address in system device tree. So in terms of the controller, we have a node describing a firewall controller, one for each in the system. Some controllers might have special controller-specific configurations. So we have a classic hash firewall cells property to define how many extra configurations there is. And each device has a firewall property pointing to the firewall controller that is protecting that specific device MMIO regions. Now, the other thing that we need is an ID space for the controller to identify the transaction so that you can say, I want to block that transaction. And the ID space is, we're calling it bus master IDs. Bus master because these are, bus masters, right? Device that can write and start the transactions on the bus. This ID identifies the device from in the eyes of the controller, and it can be unique per controller. Also, on Xilinx platforms, is always global. So here is a full example, and I think it's going to be actually quite intuitive. It's always difficult to talk about bindings one at a time, but if you see it all together, I think it makes quite a lot of sense. So in the top part, we have 2 firewall controller nodes. And each of them, firewall cells property 0 because we don't need any extra config. Here we have 4 example devices. Each of them I have a bus master ID, which is the same for each of the firewall controllers. And there is also a firewall property pointing, and this is important, right? Pointing to the controller that's protecting accesses to this region, to this MMIO region. So in this case, protecting accesses to Ethernet as a slave. This example just add one more thing that couldn't fit in the slide before, which is the bus master ID of CPU clusters. From the point of view of bus firewall, CPU clusters are like any other bus mastering devices. They can be blocked or allowed access as everybody else. So CPU clusters also have bus master IDs. So up until now, we talked about how to describe the hardware in terms of controllers, which controller protect which device, how you identify devices with bus master IDs, not about how to configure bus firewalls. And actually, domains are a really natural place to describe the firewall configuration because they already have an access list. And maybe the top reason to configure the bus firewall is really to protect that access list from other clusters, from other domains. So in order to be able to enforce this protection and set up the firewall configuration, we added a couple of properties, in particular, Firewall Conf and Firewall Conf Default, that are used to say, in short, please block this other domain from accessing my resources. We also introduced a new node called resource group to explicitly be able to share devices, memory region resources between domains, which becomes very important at the time when we are about to enforce actually accessibility in general. So the resource group is actually quite straightforward. It's just a node under domains with its own little access list, and various domains then include the resource group. So to say explicitly, I am actually using the shared resources. And this other domain is also saying, I'm using this shared resource pool. Now, how does the firewall configuration work? So a domain is going to have a new property called firewall config to say, I want to block this other domain from accessing my physical resources. Or I want to allow this other domain from accessing my physical resources. And obviously, it applies to all MMIO region of the domains, and as well as to all the bus master ID of the foreign domain we want to block access to. I'm actually going to jump directly to the example because it's going to become more obvious. So this is a domain 1, and it's saying, I want to block domain 0. It's just as simple as that. And when we say I want to block domain 0, what does it mean in practice? It means it's blocking all bus master IDs of domain 0 from accessing all MMIO regions of domain 1. What are the values? What are the commands that you can really set? Well, there is block, there is allow, and then there is block desirable. So often, and this is the case of Xilinx firewalls as well as other vendors' firewalls, the configuration table has only very few entries. So it's not really possible to say to block everything that you would like to block. So sometimes you just have to settle for the best you can do in the configuration. So for these things that would be nice to block, but they're not really critical, you can set block desirable and then give a priority as a number here. And then the software can automatically detect the best possible configuration for you to try to block as many things as you can, given the size of the configuration table. Firewall Conf Default, again, is also straightforward. It is really meant to be able to express whitelist. So if you want to block everything by default, you can either block or block desirable. You can use Firewall Conf Default and then explicitly allow only the domains that are really allowed. That brings me to slightly more complete examples of two domains that are explicitly blocking each other. So you have domain 0 explicitly blocking domain 1, and domain 1 explicitly blocking domain 0, but is block desirable rather than a stronger block. And this is another example with a resource group, and it applies seamlessly to the resource group. Obviously, if you're blocking another domain, but you have shared resources with that domain, the shared resources will remain accessible from both. And there is a possibility of even increasing the protection of shared resources, because often they're very critical. So you can even have a stronger form of block, while the other domain have just a block desirable. In the slide, I left a number of more complex examples with explanation on what they're meant to do. So if you want to dig into that, I think it's going to become easier. But I think this set of properties really supposed to be very intuitive in the way they're used. And I'll give back some time to Bruce to instead speak in more details about Lopper.
All right, hopefully everybody can hear me. So yeah, I'm just going to do a brief overview of Lopper and what it does. We've been writing it, or I guess I've been writing it for quite a while, but it's a Python 3 based tool written by a non-Python hacker. So if you go look at the source code, be gentle. But the reason that Lopper exists is that we knew not only were we going to have to do simple transformations to device trees, we were going to have to, as you can see in Stefano's examples, inevitably we were going to need to do things for different personas and be able to validate and check settings. And and we didn't want to have to write a whole bunch of custom tools, custom scripts to either look at the device tree source and grep things out, and there's things that can do this and that. So it's sort of a framework that knows very little about about device trees, and it knows even less about the bindings that Stefano was talking about. So everything that it knows how to do it's completely data driven. So it takes an input device tree, any number of transformations to that device tree, and then it will output, in the simplest case, a single modified device tree with things chopped out of it or modified or changed to be what you need to boot, say, Linux, and that's it. Or in more complicated cases, we do everything from generating Yocto build configurations to source code to whatever we want. And it does this through a series of front-end assists, back-end assists, transforms, and it can read, it can read DTS. It can work with DTBs directly. It doesn't even need the source code. And then it can do YAML sort of input and outputs. In particular, with the YAML, we are working to create some simplified descriptions, both for input and output, to avoid needing to always feed device tree inputs, because shockingly, not everybody finds writing device trees their preferred thing to do to describe a system. So that part of it is still sort of a work in progress, but the framework itself won't change to do it, but maybe some of the assists that process it will change a bit. So, all right, that's the overview. I think I guess I covered a bit of this in my description of what it can do, but some of the use cases that that we're using it for, and that it's designed for, it's this system device tree to multiple OS standardized trees, so we don't have to change the consuming operating system. Not that they might not eventually be able to read system device trees, but it's not a prerequisite for using system device trees. We can do simple add, removes, modifies. We can we can do validation and checking of inputs for the partitioning the memory of the domains. We can also do some cleanup and sanitization on output trees. for example, Lopper by default will go through and look at P handles that might or may not be missing, or things that you have removed, and it will pull out those bad references from the output tree and sort of log it and make sure it's clean. And we're getting more into, in particular, Xilinx has some examples for this, is generating device drivers and the code to support them. All right. So this is, I pulled together a few specific examples, some simple ones, some more complicated ones, and I don't think I checked in these samples, but I think I will just check them into the repository and push them up. So they'll be available for anybody that happens to want to look, because if you're like me, seeing a working example is often the best way to figure out how something works. So in this case, it's just looking to modify, you know, I put a special tag into the input tree, and I wrote a Lopper operation that would go through and delete that special tag from the node. So the CPU's node in that input tree, I didn't have room, so I summarized here, has that special tag in it, and this is just a simple operation that goes through and says, if this special tag is found in the CPU's node, delete it. And you can see I ran Lopper, and now in the output tree, that tag has been purged, and that's actually the only change that would have happened to that tree in this simple case. So, you know, we can do this. That way, we use this for either annotations or say access properties, or some of the firewall things that Stefano was describing. And in the simplest case, we can feed in a set of operations to make sure those are all cleaned out of the tree in any out of any output tree. So an operating system that may or may not know what to do with them, or if it's information you want to hide from a part of the system, it won't be there. All right. So this is I guess a more advanced one, and this is something that we did to generate some. It's similar to one I did to generate some Yocto configuration input based on a system device tree to tell us how to do a multi-config build. So in this case, it's using a few, the Lopper operations are sort of broken down into primitives. And the first one says to select any nodes under CPUs that are compatible with Cortex A72. And it also says select them if they have CPU idle states set to 3. And then the next, so that generates an internal, I guess, reference inside Lopper, where it's now tracking a set of nodes that have been selected. And then I follow up with that standard modify operation. In this case, because there's no node listed or no property listed in the modify property, it says operate on the nodes and everything that was collected in the tagged within Lopper. And so in this case, it's adding a CPU tag to the device tree node. So it's adding this priority tag, if you will, to anything that was selected. And then finally, I have sort of two following up ones that will actually just walk the tree. And we made it so you could put little Python snippets directly in your input tree. That way you don't have to go to the trouble of writing a whole Python assist. And in this case, it just goes through the selected nodes, and it prints out the ones that will have this idle state of 3 as an example of being able to walk and do output based on what was selected during the operations. And we can just skip the next select. It's just showing that it can do ORs and ANDs. And again, there's even a more complicated bit of Python code where it's looking at the outputs in a little bit more detail. And so, yeah, in this example, when I run this to count on the input tree, it says, you know, it goes through and it finds there's a single CPU at 1 that has that idle state 3, and it's been tagged with a special tag priority in this example. And the next one goes through and it finds all of the Cortex A72s in the system, or they have a PHY hand, or a node in the system has a PHY handle of 0xA. And so when you run that through, so it found 2 CPUs, and it also pulled out an Ethernet device from AMBA and then printed the node out in this example. So just something that we can do without ever needing to do Python code in a full assist, and you can just write snippets in the inputs. All right, I think I had one more. No, I didn't. Or yes, I did, sorry. And just to, I've mentioned it a few times because we're almost out of time, that there's these assists, and there's some examples in the Lopper repository, and these are where you would do more complex and sort of real logic to generate code, analyze, do things like that. And I have an example one in a tree that does a grep. And if you just skip to the next slide, what it does is this is a little bit of the implementation. It's just what you expect. It's looking for a pattern in a device tree. And I have a sample output of it on the next slide. Yeah, or not.
Oops.
Oh, intelligent. Yeah, so in this example, I just gave it that input device tree, and I said, grep for all of the compatible strings underneath CPUs. And you can see it went through and it found, you know, the CPUs, compatible CPU cluster, CPU at 0 states. And it pulled out all of the things that matched those things. And that's just a small assist that's written that knows nothing actually about the system device tree. It's being abstracted and fed the information from Lopper, and that's the output that it produced in this case. All right, that's it for me.
All right, good. So any questions? We're running out of time here, but please put in the chat window if you have any questions of this. Of course, you can go to the Lopper repository, GitHub, and look at it, look at the examples, try it out. Contact Bruce if you have questions about it.
We'd just like to thank you for your wonderful session. I don't see any questions in the chat. We will be in the Slack channel if people would like to continue the discussion or ask any other questions over there. But thanks to each of you, Tomas, Stefano, and Bruce, for your presentation and information.
Thanks, Randy.
Thank you.
See you.